So we have found the position where we have the where we found the maximum my squared plus by mz squared plus by tx squared square root. So the 1357.3 magnitude will be used to determine the minimum size of the shaft. Okay. So if we go back to week 11, I think. Okay, week 11. And if we look at, is it week 11? Maybe not. Maybe on. No, not that. Yeah, week 11, Thursday. Which we derive an expression. Okay. So now we are going to apply this formula over here. Right? Or more specifically, this formula over here. Okay, with the 1/3. I do apologize, I forgot the 1/3. Okay. So with here we can determine the radius, and this radius we derive by using 3D mole circle, or I've shown you why 2D is possible, right? So from here we can determine the radius. So this is the formula we're going to apply. Okay, so I'm just going to write here where the radius is equal to 2 over pi, right? And then the square root of my squared plus by mz squared plus by tx squared divided by the shear stress allowable. Let me make sure it's 2 over pi. Yeah, 2 over pi. And the whole thing is 1/3. So let's calculate the value out first. Okay, so this is 2 over pi multiply by 1357.3. Okay, and then the stress allowable, if the stress allowable is equal, let me look at the question. The shear stress allowable, I think, is 50 times 10 to the power 6. And then power of 1/3. Okay. So 2 multiplied by 1357.3 divided by shift pi divided by 50 power 6. Okay. Then cube root is equal to 0.0259 meters. So diameter, which is equal to twice of the radius, is equal to 0.0259. Let me put 2 first. 2 multiplied by 0.0259, right? Two multiplied 0.0259, and this is 51.8 times 10 to the power minus 3 meters. Okay, so that is the minimum diameter of your shaft. Okay. Now, for this formula over here, right? With this formula over here, we have ignored, okay, shear force and no axial loading on shaft AB. Okay. Now, I still remember telling you guys that why we ignore the shear force. This is because the shear stress induced by the shear force are small. Okay. Now I'm going to show to you, okay, is it true that it is small? Okay, you just can't take, I mean, as what is a degree all about now, right? My time, a degree is about getting a better job, is about a career, okay? Your time is not the same anymore, okay? It's not about getting a degree to get a career, okay? My time, the emphasis on career is very high. Your generation, I don't think it's as high. So the purpose of your degree is to ensure that the information that you have, okay, and the degree will give you the ability to verify whether is it right or wrong. Okay, we are in a society now that there is fake news, there are fake data. Okay, a degree, I think at your generation time, is to give you the ability to analyze what you receive from online information or sometimes textbook. Is it valid or not? Okay. So what I'm going to do now is to show you what if we did not ignore the shear force. I repeat again, what if we did not ignore the shear force? How big a difference does this make? Okay, how big a difference? Okay, so I'm going to do this now. I'm going to continue with the same example. Okay, so we are going to determine the principal stresses. Okay, we are going to determine the principal stresses. Okay, without, with, and without ignoring, or with or and without the shear force. Excuse me. Okay. Okay. So we are going to go back to, I'm going to copy this diagram over here. Okay. I do apologize, not big enough. Yes, hopefully now it works. Okay. Okay. Yes. Okay. And then I'm going to get the table. Let me shift this. And we're going to use this table. Okay. We're going to use this table. Right? Right. So the region we are going to focus on is still at point D. Okay, at point D. Okay. So we're still going to look at point D. Okay. We're going to look at point D. And we are going to select when using a 52 millimeters diameter shaft. Okay. I'm going to use a diameter shaft AB, that's 52 millimeters. What we calculate is we can use 51.8. I'm going to just use 52. Okay. So now we're going to consider the shear force, and we're going to look at point D. Okay, we're going to look at point D. So I'm going to place elements at point D now. Okay, I'm going to place elements at point D. And I'll explain why we need the elements. Okay. So this is the cross-sectional view, and we have our Y and Z, and this is position D or at point D, and these are our center lines. Okay, and I'm going to place 4 elements. Okay, and I'll tell you why. This is my element 1, this is my element 2, element 3, and element 4. Okay, and if we look at the moments, the moment about Y is acting this way, and the moment about Z is acting this way. Okay. Now this is basically at point D. Why we choose point D is because it has the higher combined loads of the torque, moment in the y-axis, and moment about the z-axis. Okay. So if we were to now, okay, at position D, right? Okay. We are going to have our element 1, element 2, element 3, and element 4. So if we look at the shear stress, let me draw a table first. Right. If we're going to look at the torque induced by Tx is equal to 596.831. Okay. They all will share the same because torque, right? Why? Because torque, the shear stress due to torque is Tr over J. Right. For element 1, 2, 3, and 4, R is constant. Right. So all these will have the same, the shear stress will be constant at element A, element 1, 2, or 3. I'm putting here they're constant. Then we are going to look at the shear, sorry, not the shear. Hold on. We are going to look at the shear stress. Now this is due to, so if you look at point D, right, we only have the shear force due to Vz at point D, right? So this is our point D. We only have a Vz, which is equal to 2487, right? Now, before we go on, Tx, the shear induced by Tx will be in this direction. This is because of the rotation of the shaft, okay? So this is our Tx rotation. Okay, so this is generating the torque in the x direction. Okay, this is the shear